All right, welcome to Talovs in Physics. So today what we're going to do is we're going to draw a free body diagram, or also known as a force diagram, to try to depict what's going on certain objects. So today we're going to focus on things that are happening more perpendicular to each other, and in a future lesson we'll look at things that are more at an angle. And so what we're going to do is we're going to switch over to document camera, and what I'm going to do is I'm going to try to create this little situation at the top. So here's the edge of, say, an ice skating pond. Here's the ice on an ice skating pond and another edge there. And so I'm going to have an ice skater, which I can't draw very well, but they're going to start. So they're going to go from velocity equals 0 to some velocity. All right. And then in the middle, let's see if I can draw. Actually, let's put skates on them. And in the middle, we'll put one leg up. And they're gliding along at a constant velocity. And then at the end, they get some, well, let's just say they hit some bumpy ice. And they start to slow down at the end. So we've got the ice skater slowing down. So slowing down at the end. And so what we're going to do is we're going to look at how to draw a free body diagram for this entire time. And so I'm going to draw 3 different free body diagrams. So I'm going to start with the one that's starting to push off. So actually, let's emphasize that, push off. So that skater's going to push off from wherever they're starting. And so what I have here is I'm going to have a force due to gravity, and that's on the skater by the whole Earth. All right, so I'm going to draw a force in the direction that where it's acting upon that. The other thing I'm going to do is I'm going to draw a little circle around this skater, because I'm going to look to see what are things that the skater is touching. So the skater is my system, and the system is represented by the center of mass dot in the middle. So I'm reducing that person down to a dot. And so force due to gravity is the one at a distance force that we're going to see here. But it's also touching the ground, right? And so touching the ground is molecules pushing back. And so we're going to call that a normal force. So on the skater by the ground. And what normal means is perpendicular. So I'm going to emphasize that right there. So it's a perpendicular force from the ground. The molecules are pushing straight up in this case because I have level, flat ground. And then I drew that right in the way, so I'm going to erase what I just wrote. And what's causing me to change speed? Well, this is my push. So I'm just going to call it force of push on the skater. And really it's by the ice, right? I'm pushing off on the ice, and it's allowing me to go forward. So it's a different force from the ice. But bottom line is this down force is going to be the same magnitude as the up force, because I'm not accelerating in an up or down fashion. But what I am is that I'm accelerating to the right based on how I drew this. So now what's happening in the middle? Well, I'll draw a little circle around this, and we're still touching the ice, but now we're not pushing, and we're traveling at a constant velocity. And so constant velocity tells me that all of the force arrows have to add up to what is a net force of 0. And so, well, how do I depict that? So I still have the force due to gravity. It's the same size as before. It's the same skater. And I'm going to have a normal force. And so that normal force is also present in this particular case. And so the normal force is going to be the same size as the gravitational force, because it's not accelerating. Not accelerating up, not accelerating down. It's just there. And so there is no push force because I'm already moving. Right? There's no motion force, no nothing like that. This is what's happening at a constant velocity. So that's what my constant velocity force diagram looks like. Okay, what about at the end when I start to hit something that's bumpy? Well, let's draw that over here. and I still have the same force due to gravity. I still have the same normal force. They're still the same size, but I'm moving to the right. I must have some sort of force that's opposing me to the left. And I'll say, since I claimed it was bumpy ice, something like that, I'm going to call that a force due to friction. And so that force to friction is in the opposite direction that I was traveling, which causes me to slow down, right? Opposite direction causes me to slow down. So basically, this is what it would look like. Here I'm pushing off to get going. Here I'm gliding at a constant velocity because I have no sideways forces on me. And here I have something that's slowing me down, which I'm going to claim to be friction in this particular case. All right, so that's what you need to put together different types of force diagrams. Essentially what you're doing is you're trying to decide, is it moving at a constant velocity or not? If it's moving at a constant velocity, all of the force vectors in your free body diagram need to balance each other out, meaning the right arrow needs to equal the left arrow, the up arrow needs to equal the down arrow. If it's accelerating, either speeding up or slowing down, then those arrows won't necessarily add up, and you'll have some sort of net force pointing in one direction. All right, so that is a real basic overview of force, free body diagram or force diagrams that are all perpendicular to each other.